The physics of modern jet combat demands the impossible. When advanced fighter aircraft converge at supersonic speeds, human reaction time and conventional mechanics are pushed well beyond their breaking points. In this explainer, we're examining an uncompromising mechanical answer to those extreme physics, the M61 Vulcan cannon. It's a masterclass in military engineering, a system that utterly defied the physical limitations of its era and remains the standard armament for the most advanced fighter platforms in service today.
To truly understand this weapon, we have to begin with a blunt, staggering operational reality. The M61 Vulcan fires 6,000 rounds every single minute. It doesn't pause, it doesn't hesitate, and it certainly doesn't yield to the traditional limitations of infantry-scale firearms.
Break that number down, and you're looking at 100 rounds fired every single second. This presents an immediate physical impossibility. We are asking a single steel barrel to chamber, fire, and extract 100 high-explosive incendiary rounds in the span of 1 second. The friction, the mechanical stress on the bolt, and the sheer thermal load would melt and destroy a conventional single barrel almost instantly. So, how exactly did American designers solve a mechanical impossibility?
We'll break down this engineering marvel in 5 critical stages. 1. The jet age problem. 2. Distributing the thermal load. 3. The external rotor drive. 4. Linkless feed engineering. And 5. Installation dynamics.
Part 1. The jet age problem. Collapsing the combat window. To understand why the Vulcan even exists, we have to shift a timeline back to the late 1940s. The transition from propeller-driven platforms to jet-powered aircraft fundamentally altered the geometry of aerial warfare. Engagement speeds doubled and then tripled. The generous firing windows of World War II, where a pilot might have several seconds to track an enemy and secure a kill, were completely gone. In the jet age, the time during which an enemy aircraft was simultaneously in range and in the crosshairs collapsed to a fraction of a second. The pilot was suddenly starved of time. During this microscopic fraction of a second, a conventional single-barrel cannon firing at 1,500 rounds per minute could only deliver about 25 rounds. At jet combat speeds, 25 rounds traveling through the air simply wasn't enough to guarantee a kill. The probability of striking a fast-moving, heavily armored jet in that window was unacceptably low. In response, the Air Force issued a requirement in 1946 for a weapon capable of delivering 6,000 rounds per minute. That was 4 times the capability of the best existing cannons.
Part 2. Distributing the thermal load, the Gatling principle.
Meeting that 1946 requirement introduced a lethal thermal problem. A single barrel cannot survive 6,000 rounds a minute. The solution they found was the Gatling principle. If one barrel can't sustain the extreme thermal load, you distribute the firing cycle across multiple barrels simultaneously. By dividing the firing cycle across a 6-barrel circular assembly, the weapon mathematically mitigates the heat. The system achieves a sustained rate of fire of 6,000 rounds per minute, but crucially, no individual barrel is ever asked to fire more than 1,000 rounds per minute. Executing this requires precise mechanical choreography. As the central rotor shaft continuously turns, each of the 6 barrels rotates through a strict, sequenced path. At any given microsecond, one barrel is feeding, another is chambering, another is firing, the next is extracting the spent casing, and the final one is ejecting it. Each barrel completes this exact sequence once per rotation. That continuous motion buys the steel precious milliseconds to cool before its next firing moment.
Part 3. The external rotor drive, removing the dependency.
But how is this massive spinning assembly of steel actually powered? This brings us to a critical engineering distinction and truly a life-or-death variable in combat. Most automatic weapons are recoil or gas-operated. They rely on the explosive energy of the ammunition itself to cycle the action. But at 6,000 rounds per minute, relying on gas pressure introduces fatal timing variables. A single dud round, a misfire, will cause a gas-operated weapon to stop dead, leading to catastrophic jams. The M61 Vulcan starkly contrasts this by using an external drive system. Powered by electric motors or the aircraft's hydraulics, the rotor turns mercilessly at a fixed rate. If a round fails to fire, the external drive simply cycles the dud round out of the weapon and chambers the next one. It forces the mechanism through the cycle without stopping, maintaining an unbroken stream of fire. The weapon drives itself entirely independently of the ammunition.
Part 4. Linkless feed engineering, supplying the beast.
Powering the rotation is only half the battle. We now have to face the next insurmountable aerodynamic hurdle, securely feeding 100 heavy cannon rounds a second into a rapidly rotating system. Conventional aircraft ammunition is held together in metal belts, with each round connected by a link that must be physically stripped away as it enters the chamber. At a feed rate of 100 rounds per second, the raw physical stress of stripping standard belted ammunition links creates immediate, fatal failure points. The metal links stretch, warp, and shatter at jet-age speeds, instantly jamming the cannon.
To supply the beast, engineers designed a highly complex linkless feed architecture. The rounds are stored in a continuous drum deep inside the airframe. From there, they travel through a flexible, closed-loop chute system, feeding directly into the rotor path without any linking metal. And furthermore, this closed-loop system crucially captures the spent brass casings and feeds them right back into the drum. You see, ejecting 100 heavy brass casings per second into the slipstream of a supersonic fighter jet would be catastrophic. The brass could easily be sucked into the aircraft's own jet engine, completely destroying the turbine blades.
The sheer consumption rate of this linkless system is difficult to fathom. Consider the ammunition capacity of the F-16 Fighting Falcon, exactly 511 rounds. Operating at 6,000 rounds per minute, the aircraft's entire combat load is violently expended in approximately 5 seconds of continuous fire. The pilot possesses unparalleled destructive power, but it is incredibly fleeting.
Part 5. F-16 Installation Dynamics, Managing the Physics.
This brings us to the severe structural and aerodynamic physics of mounting such a weapon inside a high-performance fighter jet. It's not simply a matter of bolting the cannon to the chassis. Let's break down the violent, simultaneous forces generated when the cannon fires. The recoil of 100 rounds per second creates a continuous, massive rearward thrust load on the airframe. Because the cannon is mounted in the F-16's left wing root, offset from the center of the aircraft, this recoil generates a severe yaw moment. It's a rotational force that actively tries to pull the nose of the fighter off the target. And on top of that, the high-velocity muzzle gases create an extreme pressure wave right next to the engine intake, risking oxygen starvation and a catastrophic engine flameout.
Managing these physics requires precision engineering, integrated directly into the aircraft systems. The F-16's fly-by-wire flight control computers must instantaneously and continuously compensate for the yaw moment the very millisecond the trigger is pulled, automatically adjusting the flight surfaces to keep the nose perfectly steady. Simultaneously, a highly engineered gas purge system activates. It utilizes engine bleed air to neutralize the muzzle pressure wave and aggressively blow the deadly oxygen-deprived combustion gases away from the engine intake.
Part 6. The Engineering Legacy. Smarter, not stronger.
The structural, mechanical, and aerodynamic integration of this weapon is a triumph of technical design. And its history reveals a profound irony. The core thermal distribution logic, the spinning barrels sharing a single firing cycle, was actually patented by Richard Gatling in 1862 for Civil War infantry combat. That exact same 19th century mechanical insight, refined with 20th century precision, entered service as the M61 Vulcan in 1959. Today, decades later, it remains the standard integrated armament for the F-22 Raptor, the most advanced stealth fighter ever built. Its unparalleled longevity is the direct result of an unyielding engineering mantra: distribute the load, remove the dependency, eliminate the failure mode. By distributing the heat across 6 barrels, replacing gas operation with an external drive, and swapping jamming belts for a linkless feed, the engineers systematically eradicated every variable that could compromise the weapon in combat.
The ultimate solution to the jet age problem was not found in brute force. The designers didn't seek out stronger steel. They didn't invent a heavier barrel or a more powerful explosive to cycle the action. They recognized that individual components possess hard physical limits that cannot be overcome by simply scaling up the material strength. Instead, they adhered to a stark, foundational philosophy of military science. True engineering builds systems smarter than the problem. The M61 Vulcan remains a masterpiece of extreme problem-solving because it forces 6 components to share a burden that would destroy any single one of them. It is a clinical, devastatingly effective machine. But as aerial warfare continues to evolve toward directed energy and hypersonic engagements, one has to wonder, will the Gatling principle finally reach its mechanical limit, or will this 19th century logic find yet another way to dominate the skies of the future?